Welcome to the first part of this video covering Chapter 2, segments, specifically Lesson 1, real number subsets, and the number line. The number line portion will be found in the second video. Okay, hopefully all of these vocab words look familiar and that you are ready with your paper notes there to be copying this down. Obviously, if you need to pause the video at any point to catch up with the text, please do so. The first one is natural numbers. Our first vocabulary term is natural numbers. These are also referred to as counting numbers because when you were first learning to count things whenever you were a baby, you started with the number 1, 2, 3, 4, and so on from there. They're called natural numbers because these are the numbers you can find in nature, starting with the number 1. Our second vocab type of subset of real numbers is the whole numbers. These are natural numbers and 0. So you may have been thinking back with the natural numbers, well, it starts at 1, 2, and 3, and so on. Well, what about 0? 0 is technically a number that you cannot count. You did not learn 0 whenever you were first learning to count because you don't know how to understand 0 fingers. You start with finger number 1. So that's why these are the natural numbers. You learn to count with them. But whole numbers are 0 and then positive, and really through positive infinity, just like the natural numbers. Integers are the most common, but these are also the ones that we often call whole numbers accidentally or without thought to it. These are our positive and negative whole numbers. So we're now starting at negative, really kind of negative infinity, but only with those whole numbers, including 0, and now also the positives going on forever, again, just in those positive and negative whole numbers. Rational numbers are considered a ratio of two integers, any repeating or terminating decimal also. And this is a good time to notice that the natural numbers are the smallest here. It's just the shortest definition is counting numbers. But now if you look at whole numbers, the whole number definition includes natural numbers, okay? And then the integers are positive and negative whole numbers. Well, there's the whole numbers, which are the natural numbers, and then the rationals are the ratio of two integers. So integers, whole numbers, natural numbers, they're all connected. The decimal part here mentioned with rational numbers is simply because any repeating or terminating decimal can be written as a ratio of two integers. Now, a ratio of two integers is just a fancy way of saying fraction. So when we talk about our rational numbers, we are talking about our fractions. The final subset are the irrational numbers. They are any non-repeating and non-terminating decimal, and also any non-perfect root. The concept of this bolded "and" here is because it has to not be repeating and not ending. Because if it's not ending, it means it's going on and on forever, but technically repeating decimals also go on and on forever. So it cannot end, but it is not allowed to repeat. Those sorts of decimals are any sort of non-perfect root. All right, so on the last slide, I kind of talked about the connection between natural numbers, whole numbers, integers, and the rationals. Irrationals did not mention anything about rational numbers. They're actually quite the opposite of rationals. That's why they're irrationals. So all of these are considered rational numbers, and then there are these irrational numbers. So the actual definition of real numbers is the set of all rational and irrational numbers, and that should say of, not of. And so what I want you to realize is that there's really two different sections here. These are all connected. This is its own little bubble, but these are all subsets of the real number system. Any number that you can possibly think of can fit somewhere into one of these subsets. One final piece to these subsets and of the real number system is that there are letters used to represent these words in case you don't want to actually spend time writing out the whole word, and that happens a lot with me. I don't always write out the word, so I want you to have this written down. N is used to represent the natural numbers, W is for whole numbers, that seems pretty self-explanatory. Z is for integers, and Q is for rationals, and that goes back to the words in a different language, Latin or Greek, I don't remember. And then we have irrationals, and then our real numbers are the R. And actually, they're supposed to be more bolded where there's like this thicker side there, like a thicker side here. The Z is thicker in the middle. The Q has the thick side there. So just something to consider. The real numbers, like when I actually write out the real numbers, I write it like that. So that bolded side there. But those are some letters that you can use instead of writing out the whole word. So what we're going to do next is we're going to fit all the real number systems and the subsets into this diagram that most accurately represents how the system and the subsets work together. So you will need to draw this yourself on a piece of paper if you do not have this sort of diagram already in your possession. I don't want to take real long here and read all this to you. Please pause the video at some point and fill in how this Venn diagram works with the definitions. The only thing I do want to point out is the flow. Like the counting numbers is the smallest bubble because all of them fit inside of the whole numbers. So that's why the definition for whole numbers is natural numbers and zero. Positive and negative whole numbers for integers. That's why the whole number bubble is inside of the integer bubble. So there's a reason why they're all inside of each other like this, because that's how the rational numbers work. And then you'll notice that the irrational numbers is its own little bubble out here because they're completely separate, other than the fact that they all belong to the real number system. Okay, so -6 would belong as an integer because it is a negative whole number. 2.73 is a rational number because it is a terminating decimal. 3/7 is also a rational number because it is a ratio of two integers. The square root of 2 is irrational because it is a non-perfect square. The square root of 9, however, is actually the value of 3. So the square root of 9 is 3. So that is actually a counting number. So I'm going to put this weird square root of 9 here. But please understand that since I'm putting it in this natural number bubble, it is also a whole number. So the square root of 9 is natural and whole and an integer. And the same thing here. This -6 is an integer, but it is also a rational number. Okay? So -100 would be an integer, which is also a rational number. 0 is the only number. 0 is very interesting because it's the only number that lives in this section of this bubble here, because the whole number definition is natural numbers and 0. So 0 is the only number that's not a natural number, but it is whole. Pi, this symbol next to the 0 there, is also an irrational number, so I'm going to put pi out there. 1 is, let's see, put that as a whole number. Well, we'll put it as a natural number because then it's automatically a whole number too. So the number 1, like I almost put it in the whole. Yes, 1 is a whole number, but only because it's technically a natural number. -1/2 is a rational. I know it may seem weird that I'm putting a negative number in the rational, but it is a fraction, so that's really what's putting it there. Same thing with -3.8, also a rational number. 5.42, since the 42 is repeating, that puts it as a rational number. And when you see something like this last number down there with the ... that means that it's going to be continuing in this same fashion as it already is. It does not mean it's going to be repeating. If I don't see a repeating pattern, then it's going to continue without a repeating pattern. If there is a repeating pattern there, then that repeating pattern will continue. In this case, this number 8.293017 does not have a pattern, so it will continue without a pattern, making it irrational. So please include that in the irrational bubble. Okay, all in all, this Venn diagram is used to classify numbers within the real number system. So you notice this definition up here. It's the set, again, of all rational and irrational numbers. That's what a real number is. Any number that you can think of fits somewhere in this Venn diagram. Okay, when you go to classify a number, you want to look for the most specific one. Like this square root of 9, I said is 3. Yes, it is 3. and a 3 is a natural number, which makes it a whole number and an integer and an irrational number, and therefore a real number. It's not irrational, but it is all of those other things. The most specific, most correct answer would be a natural number for the number 3. So the only time that I would want to list all of those is if the question asks me to list all of the subsets that the number 3 belongs to. Otherwise, if it's just asking me to classify, the correct answer for the value of 3 would be that it is a natural number. Okay, so this chart is going to examine that a little bit further here. The number -7, we're going to just go down the chart here, which really is those bubbles from smallest to largest. Okay, well, and then the irrational numbers are its own bubble to begin with. So the number -7 is not a natural counting number. You do not learn to count -7 when you are a baby. It is not the 0 or all these natural numbers. The first column that I can put -7 in is an integer, which means it's automatically a rational number, which means I skip irrational and just go straight to real. The number 3/4 is a fraction, so that puts me straight at rational and real. Okay, so go ahead and see if you can finish off this chart. Go ahead and pause the video, finish off this chart in your notes here, and compare them in the next couple seconds. So here's that chart completely filled out. You'll notice that the number 5 has all of them completed. So if you were to have to put a mark for each of the subsets or to identify all of the subsets for which a number belongs, then you would list them all out. If you were just classifying the number 5, the number 5's answer would be natural number. The number 0.398 would be a rational number. Square root of 2 is irrational. 3/4 is rational. -7 is an integer. So we're going to the smallest bubble that they're in whenever we're actually giving it a name. So using your knowledge now with the Venn diagram and how the real numbers all work together, I'd like you to go ahead and give these problems a go, true or false. If false, explain why, or come up with some sort of counter example. And then if you just pause the video, you'll be able to check your answers here in a couple seconds. All right, almost done here. As we take a look at rational versus irrational, I'm just going to use my letters here. Rational is Q, irrational is I. And so just some examples here. A rational number can be a negative whole number. It can be an integer. It can be a fraction. It can be a decimal that ends, so 0.05. It can be a decimal that repeats, so 0.05 with a repeating bar over it. Okay, but an irrational number is something like pi, or the square root of 5, okay, or the square root of 8. These are all numbers that are not perfect squares. There are a couple other letters, but even just a decimal that goes on forever. We saw something like this earlier, like that without a pattern. So notice, as I'm completing this chart, there's nothing in here. They have nothing in common. They have nothing in common. This is a Venn diagram proving that these have nothing in common. And if you look back at the diagram that we did with the real numbers, again, the irrational numbers were its own little bubble. The rationals were its set of relationship with bubbles, and they were all inside of real numbers. So yes, they are all real numbers, but they have nothing else in common. So I'll add that in there. Have nothing in common other than being real. Being a part of that real number system. To wrap up this section of the notes, I want you to go ahead and do these last 4 problems on your own. So for all of these 4, you are writing a number with 10 digits after the decimal point that satisfy each of those given situations. So you're doing that on your own, and this concludes the first video for this lesson.